Okay, so this is going to be the start of the material for the next exam. So this is material for exam 2, and this is the second part of chapter 9. We'll spend some time talking about reaction rates and rate laws, and then we're going to talk about integrated rate laws in the next session. So what's a rate law, and why do we need to know? Well, we can talk about how fast a reaction moves, the speed of a chemical reaction. That's called the reaction rate. And that reaction rate is a measure of how fast it makes products or it uses up the reactants. And so we can control that, and the way that we can control that is through a number of different mechanisms. We'll talk about those. So if you look at this reaction, right, you've got H2 plus I2 going to form 2HI, right? So how do we talk about this in terms of defining a rate? So the rate is the change in the either reactant or product, right? And remember, H2 was one of the reactants. And so if we're looking at H2, then what we're doing is we're looking at how H2 is disappearing, right? And so that's why we've got that negative sign there. So how quickly is it disappearing? And it's that change in concentration over the change in time. And so you could pick any point in time, right? Time 1, time 2. And then you would look at the concentration at each of the times. So it's measured in concentration of reactant decrease or in product increase, and it's over this amount of time. And again, this negative sign is really important because that says that you're looking at the disappearance of reactants. The average rate of reaction, right? The rate of the reaction over the course of time, right? And so if you look at these time factors, we've got time from 0 up to 100 seconds, and then these increments of 10 seconds, and we can look at those rates throughout, but then we can also look at an averaging of those rates. So the function, right, the reactant and product concentrations are a function of time, and if you look at the increase, that is going to be the product, right, and if you look at the decrease, that's the reaction or the reactant. And we can look at those at any point in time, right? And so this is talking about a 40-second increment and the change in concentration over the course of that time. Okay, so we can take the tangent at any point, and we can look at the instantaneous, what we call the instant reaction rate. The reaction rate is going to slow down because the concentration of reactants is decreasing, right? And then at some point the reaction is going to stop, either because the reactants have run out or because the system has reached its equilibrium. And at equilibrium, it doesn't mean that all of the reactants have been used, right? The coefficients, right, of balanced equations are not always the same. And so to be consistent in the way in which we describe reaction rates, the change in the concentration of each substance is multiplied by 1 over that coefficient. So, for instance, if we take this generalized form of a reaction, little a being the coefficient of big A, little b being the coefficient of big B, etc., then the two reactants is it's negative 1 over little a, right, times the concentration of, or the change in concentration of A over the change in time. And then on the product side, right, it's 1 over C times the concentration of, or times the change in concentration of C over the change in time. So the average rate is the change in measured concentrations in any particular time period. So in other words, the average rate can be averaged over an entire time interval, right? Or it can be smaller time intervals. The more the average rate deviates then from the instantaneous rate, that means that you're taking a larger time interval. If you're taking very small snapshots, you're talking about instantaneous. The instantaneous rate, on the other hand, is the change in concentration at any particular point in time, right? So it's the slope at the point on the curve, right? And the instantaneous rate is determined by taking the slope of the line of tangent to the curve at that particular point. And you can remember that the first derivative of a function is a calculus, it's a term in calculus for change of x over change in y, right? So when we want to look at these rate changes, right, we can talk about the different rate changes according to the reactant H2, right? And we talk about instantaneous rate. And for looking down here, this is that instantaneous rate, right? The tangent, the line of tangent that we just drew, shows that there was a minus 2.8, right? And that was over a 40-second time interval, and so you get a rate of 0.0070 molarity per second, right? On the other hand, and that's a negative, right? On the other side of this, because of the 2, remember that 2 there, right? You can get an instantaneous rate that says, okay, now this is 1 over 2 times 0.56 over 40-second, right, time interval. And you get a 0.0070 in the opposite direction. Okay. So how can the reaction rate be affected, right? And what are the effects? Well, the reactants, the nature of the reactants is essentially what kind of reactant molecules and what condition are they in. Right? So if you have a small molecule, it can tend to react faster than larger molecules because some of what happens is orientation driven, right? Gases are going to react generally faster than liquids, and liquids react faster than solids. Powdered solids are going to be more reactive than solid blocks. More surface area means that there's more potential for reactants. Certain chemicals more reactive than others. Okay, potassium metals are more reactives than sodium metals. Ions are generally react faster than molecules. And that's usually because bonds do not need to be broken. What are the factors that are affecting reaction rate? Temperature, right? Temperature is a biggie. And temperature, increasing the temperature is going to increase the reaction rate. And just a rule of thumb is for each 10-degree rise in temperature, the reaction should double for many of the reactions. But there's a mathematical relationship between the absolute temperature and the speed of a reaction that was discovered by Arrhenius, which will be examined in the next portion of this. You can affect the reaction rate by introducing a catalyst. Okay. And catalysts are substances that speed up the reaction, but they're not consumed. They're not actually a part of the reaction. They're just speeding it up. Positive catalysts are the most common, but you can in some cases want to slow a reaction down. You might imagine reactions that just get too hot, and you want to slow that down so that there's some time for the heat to dissipate. There are homogeneous catalysts that are the same phase, so a liquid with a liquid a gas in a gas. They're heterogeneous, where it's in a different phase, where you might have a liquid flowing over a solid catalyst. And how they work, I'll talk about that again later. Reactant concentrations. Now, this is one that is part of what we're talking about now, where we're gonna create these rate laws that tell us how reactant concentrations are affecting the rate of reaction. So, in general, the larger the concentration, the faster the reaction. So that increases the frequency of collision, right? Molecular contact. And concentration of gases depend on the partial pressure of the gas, and so that's one of the reasons that we worked through all the partial pressure stuff in the previous section. So a high pressure then would lead to a higher concentration. And concentrations of solutions depend on the solute to solution ratio, or in other words, the molarity. So the rate law. The rate law is something that we're going to use to describe how each component is affecting the reaction. Okay? And the rate law has to be determined experimentally. There's no other way to determine the rate law. The rate of the reaction is directly proportional to the concentration of the reactants, and then what we're going to show is that it's going to be raised to a power. Now, the power, right, is called the order of the reactant, and then there's also a constant involved, right, that is part of describing the rate. And so down here in red is the rate that is equal to that constant times the concentration of A raised to some power m, the order, times the concentration of B raised to some power n. Now, these can be any number, including 0, right? So in other words, they can not have any effect on the reaction rate. So how do we then determine this? Well, most of the time it's spectroscopically. And so what we can look at is the concentration of a given reactant, and then we can look at that initial rate. Right? So what happens when we go from point 1 to point 2 to point 4? That reaction rate doubles from 0.015 to 0.030 up to 0.060. Right? So you would say that the rate with respect to A is 2 because it's doubling, right? But we can also have, like I said, 0 order. So in other words, A can have no effect on the initial rate. Okay? So again, at point 1, 0.015. At point 2, 0.015. At point 4, 0.015. So if the reactant A is having no effect on that initial rate, then it is a 0 order. It is contributing in terms of 0 order. Right? On the other hand, it can be second order. Okay, and when I said the doubling, right, is actually first order. Right, second order is raised to the second power. Right, so it is the concentration of A to the second power. And so that's really important to recognize, because as you go from point 1 to point 2, doubling the concentration, but you're going from 0.015 to 0.060, which is raising that rate to the second power. Go from point 2 to point 4, you go from point 0.06, take it to the second power, and it goes up to 0.240. Okay. So reaction order, right? Reaction order is determined again by the power in the rate law. Okay, so this rate is written as K times the concentration of NO to the second power, okay, times the concentration of O2. Now this is assumed to be then the first power, right? Because there's no, we didn't put a superscript there. So it's second order with respect to NO, and it is first order with respect to O2, but the overall rate is third order, right? Add them together. All right. Let's look at this. If we're looking at data, right, and we're doubling NO2, what happens to the rate? Right? The rate goes up by a factor of 4, so that makes the NO2 affect 2, right? If we then look at keeping these two the same and doubling here, we kept these two the same, these two the same in the first one, and doubling here, what happens? Nothing, right? So this is actually 0. Right, we can look at that again when we go doubling here, and what happens? We go up by this factor of 2, and then this has a contribution of 0. Okay. So let's see what we can do with a few of these. Okay, let's look at the rate order of this. All right. So we're taking NO2, and we want to look at what happens when we double the concentration of NO2. Right. Again, this is remaining constant. It goes from 0.26 to 0.051, right? So it is times 2, which equals an order of 1, right? Because every time you double this, you double that. If we look at going from, let's see, 0.2 now, and we went from 0.01 here to 0.2 here, and these two remain the same. We went from 0.51 up to 0.103, and that's a doubling, right? So this was times 2, which means that it's a rate of 1, right? If we look at both of them going up, we went from 0.1 up to 0.4. That's 4 times. That makes sense, right? Because of 1 and 1. Okay? All right, let's look at this one. So as we go from 0.050 up to 0.1, what happens to the rate? It goes from 0.14 to 0.29. That's just doubled, right? So we doubled the concentration over here, and we doubled the rate. Therefore, it's an order of 1, right? So now let's look at doubling the concentration of the Cl2. And we do that, we go from a 0.029 up to a 0.041. Again, that's not quite doubling, right? So if we took a calculator quickly, get my calculator, and I say 0.041 divided by 0.029, it's about 1.4, right? So we can actually have a 3 halves. Right? This didn't just go up by 2, it went up only by 3 halves. Right? So we might consider that in a later, right? Or we'll talk about that in class. So let's talk about determining rate laws from the initial rate reaction. So the rate law, the initial method, the rate law must be determined experimentally. The rate law shows how the rate of reaction depends on the concentration of reactants. And changing the initial concentration of the reactant will affect the initial rate, right? So we looked at all of those factors. Then if the reaction is zero order, the rate of the reaction is always the same. So doubling A will have no effect on the rate. Okay. If it's first order, the rate is directly proportional. It means when you double the concentration, you double the rate. If it's second order, doubling the concentration actually quadruples the rate. Okay? So if there are multiple reactants, then experimentally you have to change those reactants one at a time, right? One has to remain constant while you change the other one. So you change the initial concentration of one, look at what happens, change the initial concentration of the second, and look at what happens. And that's what we were doing in those slides where we were determining the rate of each of those. All right, so that's it for this first part of reaction rates. The next one is integrated rate laws, and we'll get to that a little later.